This video is going to pick up with the last two periodic trends. So the first video talked about what a trend is in general and then talked about the atomic radius trend. This video is going to talk about ionization energy and electronegativity. So go ahead and open up your foldable and let's start with ionization energy. So I'm going to be writing this like this part is on the top of the foldable and then this part's on the bottom, just to give us some more space. Okay, so for ionization energy, let's talk about what that is first of all. So ionization energy, we're going to be doing something to form ions, the energy it takes to form ions. And specifically, we're going to be looking at forming cations. So that means it's the energy it takes to remove an electron. So it's the energy required to remove an electron. And whenever we are removing an electron, that means now we have lost electrons. So losing electrons, that falls under the category of cations. So we are looking at the energy it takes to form cations. So really, even though it's ionization energy, it really could be like ionization energy. Okay, let's talk about what happens across a period and then within a group as well, just like we did last time. So we're going to start with going across a period, and we're going to look across our second period. So our second row is where we're going to be looking. So let's just take a sampling of these. Let's look at lithium, beryllium, fluorine, and neon. So for the period trend first, we are going to look at, we said lithium, and then beryllium, fluorine, and neon, and that's just a nice sampling across. And we're going to talk about them in terms of valence electrons, because when we are talking about ions form in order to become stable, such as a noble gas, right? They want 8 valence electrons. So this game is all about valence electrons. Lithium only has 1. Beryllium has 2. Fluorine is a little bit happier. It has 7. And then neon is perfectly stable. It has 8 valence electrons. So if we're looking at the energy it takes to remove an electron, we want to look at how badly do these elements want to hang on to their electrons. So for example, we have something like lithium. Lithium doesn't even want to keep this electron. It really wants this electron to be removed. So lithium wants 1, I'm going to put VE for valence electron, removed. So if that's the case and lithium actually wants this 1 valence electron to be removed, it's going to be really easy to remove that electron, because as soon as lithium removes that electron, now it becomes like helium's noble gas configuration. So lithium really wants that electron removed. So that being said, it's going to be very, very easy to remove that electron from lithium. Super easy. Let's look on the flip side and talk about neon. So neon currently has 8 valence electrons. Neon's already stable, and we know from our lesson about ions that noble gases don't even form ions. So if we try to go up and take one of these electrons from neon, it's going to be like, you're not getting my electron. You would have to fight tooth and nail and then even more to get this. So it is really, really, really difficult to remove an electron from neon because it's already stable with its 8 valence electrons. It does not want one to be removed, so that would be very, very difficult. And then our other two are somewhere in the middle here. So fluorine, it has 7 valence electrons. In fact, fluorine doesn't want one removed. It actually wants to gain an electron. So to try to remove one of its 7 when it's so close to being stable, it's not going to have it. Does not want that. So it would also be really difficult. So let's talk about what this means in terms of low and high energy. If it's easy to remove an electron, it's going to take low energy. And specifically, this is ionization energy to remove that electron. Whereas neon, on the other hand, is going to take high energy because it's so difficult. It doesn't even want to give up that electron. It's stable. And then something like fluorine would also have very high ionization energy. It's going to be very difficult to remove that electron. So on our periodic table here then, we already know the trend for the period, and we're going to draw it from low to high. So for the period trend going this direction, we have high ionization energy over here, and we have low ionization energy over here. And that'll be true for every period. Rubidium, it's gonna be a lot easier to remove an electron from than iodine or xenon, something like that. Okay, next up, we need to talk about the group trend. So we talked about the period trend. Now let's talk about what happens within a group. And we're just gonna look at our first group here for this trend. And we are going to start with, let's say, lithium, and then let's pull out just a couple of the other ones here too. So we know that lithium has, if it's a neutral atom, it has 3 electrons. And then let's just jump down to potassium. Potassium has 19 electrons. And then all the way down to francium, Fr. This one has 87 electrons. So let's talk about what that means in terms of removing an electron. If we look at francium, francium down here has 87 electrons, which means we have tons and tons of rings, right? Francium has 7 rings, right? It's on the 7th energy level. There are just a ton of electrons in there, whereas lithium only has 2 rings. So to remove an electron from something like francium, where there are so many energy levels, it's not as big of a deal compared to lithium, where there's only 2 energy levels. So that being said, it's a lot easier to remove an electron from francium because we already have all of these other energy levels there, whereas lithium, there's only a couple. So lithium's really going to notice if one of its 3 electrons disappears, whereas francium's not going to notice as much if one of its 87 electrons disappears. So lithium up here is a lot more difficult to remove from. And we know that difficult means that it takes some higher ionization energy. So this is higher energy to remove. In francium, it is going to be easier to remove that. So it's going to take lower energy. So let's go ahead and label that on our periodic table. So we know that within a group, I know that we looked at this group over here, but I'm going to label it on this side. So we have higher ionization energy at the top of the group and lower ionization energy at the bottom. So this one is also high here, and it's low down here. So for every single group, towards the bottom of that group is easier to remove from than the top. So like bismuth would be easier to remove an electron than nitrogen. So overall, if we're looking at an overall trend, our trend goes this direction because we've got low on this side and low at the bottom, which means this is the lowest overall down here. And then we are the highest overall up here. So to kind of summarize that then, we notice that over here, the element with the lowest would be francium, and then up here, the element with the highest ionization energy would be helium. So if you were looking at some different elements and trying to figure out, like ordering them from lowest to highest or highest to lowest, you would just want to follow this gradient that we see here. So let's say the elements were phosphorus, cobalt, oxygen, and strontium. So to order those from lowest to highest ionization energy, we would just be following this line. So we'd be going strontium's the lowest, then cobalt, then phosphorus, then oxygen. So whenever you are trying to order elements, just look for that overall trend of that arrow of what's happening. So to summarize ionization energy, it's the energy required to remove an electron. So we're looking at the energy it takes to make a cation. We notice that going across the period, it gets more difficult because our valence electrons increase, becomes more stable. And then down a group, it's easier. So at the top of the group, it's more difficult. At the bottom of the group, it's easier to steal that electron. So overall, we notice that helium has the highest ionization energy and francium has the lowest. Okay, up next is electronegativity. So just by looking at that name, we know that's going to have something to do with electrons, and electrons carry a negative charge with them. So we know we've got something about electrons and their negative charge. Electronegativity is the tendency of an atom to attract electrons. So atoms will attract electrons depending on a few things, and it depends on how many electrons they have and how many of those electrons are valent electrons. So we know that elements want to have 8 valence electrons. If they don't have 8 valence electrons, they're doing everything they can to get them. So because of that, something like the noble gases that already have all of their valence electrons in full, they do not participate in this trend. They are already stable. They're not going to attract any more electrons. They are happily full. But let's talk about what happens across a period first. So we're going to talk about the period trend first for this one, and then we'll talk about the group trend. So we're going to look at valence electrons just like we did in the last one. So we're going to go across this row right there, just pick out a sampling. So let's take a look at sodium, aluminum, how about sulfur and chlorine? Because we're not choosing from the noble gases. They're already stable. Sodium has 1 valence electron, aluminum has 3, sulfur has 6 valence electrons, and chlorine has 7 valence electrons. So based upon this information, we're going to look and see how likely, what is the tendency of that atom to attract other electrons. So let's first look at what each of these elements wants to do to become stable. So to become stable, sodium, it really wants to give away 1 electron. I'm going to put VE for valence electron. And that's to be stable. It really wants to give that away, right? We know that sodium typically forms a 1+ ion because as soon as it gives that valence electron away, it's now like a noble gas. Aluminum typically forms a 3+ ion, so it wants to give away 3 valence electrons. Sulfur, on the other hand, it typically forms a 2- cation because it's only 2 electrons away from becoming stable. So it really wants those other 2 electrons. So it really wants to get 2. It really needs 2 valence electrons, and then it's stable. Chlorine is even closer. Chlorine just needs that 1 other valence electron, and now it's stable. So in terms of attracting other electrons, if we think about which one wants to gain another electron, we're really looking at chlorine, because as soon as chlorine gets that other valence electron, it's stable, it's full. If something like sodium were to get 1 other electron, it's like, so what? Great, now I have 2. I still want to get rid of both of these because I would rather get rid of my electron. Because of this, chlorine wanting to gain another electron really badly, it's actually going to attract electrons more than something like sodium. So chlorine is very, very close to 8 and needs 1 more, so it's going to attract electrons more than something like sodium. So because of that, it has a higher electronegativity. It's going to attract the electrons more. It really wants that other one. Sodium is not going to attract another electron because it's trying to get rid of it. So because of that, it's going to have a really low electronegativity. So if we draw our period trend, it's going to look like this. Remember, we're stopping at the halogens. We're not going all the way to the noble gases. It's going to be low over here and high over here. And that'll be true for any row. We chose the 3rd row, but if we look at the 2nd row, something like lithium, it also wants to give its valence electron away. It's not going to attract more electrons, but fluorine, it is so close to having a full shell, it's going to attract electrons a lot more. Okay, let's talk about the group trend next. That was the period trend. Let's talk about the group trend, and then we'll put our concepts together. So for the group, let's look at our first group here, and we're just going to pick out a couple of these. So we're going to look at the same ones that we did before. So all of these in group 1, these all have 1 valence electron. So technically all of these are trying to get rid of their electron, but let's see what happens as we are going up and down a group. So francium down here, just as we said up here, it has a ton of energy levels already. It has a lot of electrons. So if it attracts 1 more, francium's kind of like, so what? I already have 87. What's 1 more? It's fine. But lithium, on the other hand, if lithium got another electron, it would be like, okay, that actually makes a difference because it only has 3. So because of the amount of electrons between these and the amount of energy levels, we can see a trend. Something like francium, it already has a ton of electrons. It's not going to attract any more. Lithium would be more likely than francium to attract electrons because it has fewer of them. So that being said, lithium would have a higher electronegativity and francium would have a lower electronegativity. So let's map this. We know as we go up a group, and granted we did the group over here, but we'll draw it on the other side because it'll be the same. It's higher at the top of the group and it's lower at the bottom. So now to draw an overall arrow, let's put our period and group trend together. Our overall arrow is going to start at francium and point up towards fluorine, where we have an overall low electronegativity here and a high electronegativity over there. So our lowest electronegative element would be francium. Our highest electronegative element would be fluorine. So let's jot that down. So francium, Fr, has the lowest electronegativity, and fluorine has the highest electronegativity. And then our noble gases, they don't attract any electrons whatsoever. So they do not participate in this trend. Okay, let's recap electronegativity. Electronegativity is the tendency of an atom to attract electrons. We know that as we go across a period, we have more valence electrons over here than over here. So because of that, more valence electrons means a higher electronegativity. It's closer to being full. As we look at the group, the top of the group, we will have a higher electronegativity than the lower due to just the number of those core electrons in the center of the atom. And we know that overall, francium has the lowest electronegativity and fluorine has the highest electronegativity. Okay, that wraps up all 3 of your periodic trends. So you now know atomic radius, ionization energy, and electronegativity.